Hi there, my name's Gary and I'm going to be walking through how to read your stats textbook starting with section P2. So in this demonstration I'm just going to show you how I read the book, how I effortfully read the book and use the resources in our book and mainly the Google to try to kind of dig deep into what's going on. So we're going to start with section P2 called Exploring Data. So it says in this section, we're going to look more closely at step 3 of the 6-step statistical investigation method. So just starting off with this book, I know that was in P1, it sounds familiar, but I don't exactly remember the 6-step statistical investigation method yet. So as soon as I hit that piece, right, starting at this first sentence, step 3, I don't remember what that is. So I'll write step 3 down. And then what we're going to do is we're going to go back into the previous section, section P1. So if you have the book, you'll be flipping back. Although you can do this all on Y+ if you have the book there. So we scroll down, we see 6 steps of a statistical investigation, and we see right here step 3. So step 3, explore the data. Well, that's good. That's the section that we're in now. But more closely it says we're going to be looking for patterns. Okay. And that's related to our research question. And as well as we're going to look for unexpected outcomes that might point to additional questions to pursue. So also unusual outcomes. Okay, so great, we know what we're doing. So we go back to our P2 and we say, okay, this is what we're going to do today, and we're going to do it using this Old Faithful example. So specifically though, if we go back, it mentions in this example we're going to encounter data from a natural data generating process, okay, that repeats the same random event many times. So as soon as they put quotes in a book like this, if they put quotes around something, that means they're trying to give us a little foreshadowing. So, and this is an important idea that's going to come up again. And we're just going to look at this as a specific example now, but it's an important thing to try to think about that. And they also do, so they do data generating. So we can check that out. Okay. And then they also put into brackets here, it says, which allows us to see a pattern, and in brackets, a distribution. So again, you might be thinking reading this, why keep calling things 2 different names? Why can't we just say a pattern instead of a distribution? Or why can't we say a process instead of or something, a process that repeats instead of a random event? And we'll see it's a good idea to have more general names for things so that we can apply them to many different scenarios. And so having these more general names like random event and distribution is just nice so that we can all talk to each other using this kind of common language. So okay, we've got some ideas of what we're looking at here, and now we go down and we see Old Faithful. So it gives us a little info on Old Faithful. Nice little picture here. It says, millions of people from around the world flock to Yellowstone Park to watch the eruptions of this geyser. Okay, so we're going to be looking at, if we go back up, a data generating process. So this geyser is erupting, and somehow we're going to get data from this. Okay, and if you know anything about Old Faithful, it just keeps going. So this is probably going to be their random event that goes many times. All right, and then we're just looking for a pattern, because step 3 says we're looking for patterns in a process or in data. And so right away we're going to say, okay, hopefully we can get some data out of this and then find some patterns. All right, so if we go down a little bit as we're reading through, they ask some questions for us. So maybe you've already thought of these questions as you're reading. How faithful is it? How predictable? How long do you have to wait between eruptions? Can someone tell you exactly, or can they only kind of guess? So what we're going to do is try to explore some of these questions by looking at the data. So if we scroll down, you read through this, they give us some data. So 222 eruptions of Old Faithful taken over a number of days. Okay, so we got 222 eruptions. Great. And then right away, which is a great first step for lots of different things we're going to do in this class, is we're going to visualize right away. All right, we're going to get a distribution, just to throw that word in at you. So what we're going to be doing is trying to investigate this picture here. So one thing you may want to do in your notes is, it doesn't have to be perfect exactly, and you don't necessarily have to do this, but you'd like to have this picture as you're looking through the rest of this. And, depending on the way the book is exactly laid out, you might have it open the whole time. But if not, you may want to take a picture of this or, give yourself the general picture on your own page. Luckily, if I can get this to work, I can take this and put it on my own notes pretty nicely. So let's see if I can do this here. Oh, there we go. And then I move it down. How's that going to go in there? Perfect. So I'm going to put it over here, and that just gives me another reference for it. Okay, so we see each dot on this dot plot. Okay, that's a different eruption. So we also see that what they did was they recorded the time until the eruption in minutes. So you want to be really particular about this. When someone gives you data, one of the first things you want to do is say, okay, what are the units on this data, if it makes sense to ask units. So if we have a quantitative variable, it's a number in some way, that can have units on it, and the units can give you a really good idea of what's going on when you look at the data. If this is in hours, then that says a very different thing than if each of these dots represents minutes. So we look through here, we see, okay, it has an okay shape to it. There's a lot of dots. They're kind of spread out all the way from just over 40 minutes to the biggest one being 95 minutes. And so we're going to have to think, what tools are we going to have now or develop so that we can try to extract some information out, so we can answer, if we go back, any of these problems in this paragraph. Like what can we know about this? So before we get to any of that, the book has a stop and does a think about it. So we want to keep practicing these ideas, and it's going to happen throughout the entire course. What are the observational units and variable in this study? So we want to try to do this for every problem we get, every type of data, anything that gets thrown at us that's statistics. One of the first places to start is, what are your observational units, what's your variable, and what type of variable? So, observational units. If you remember what those were already, and you can answer that, that's awesome. But if you can't, we can go back, because you always can go back and look. So if you have the book on you, what you can do is you can go into the back and you can just look up observational units, and that'll tell you where it is. If you don't, then you have to kind of just scroll through, and sometimes scrolling through, if you have a good idea of where something is a pretty good method. So let's see here. We go down to this, can't find it. Terminology, boom. So in this book, they do a good job, for the most part, of saying, here's the terminology, and here's a little header for it. Let's look there. So if we go back, we see the individual entities on which data are recorded will be called the observational units. Okay, so we have to think about, how are we getting data here? All right, so hold that for a second. And let's go back to our exploring data. So we scroll down, let's give some more room here. Okay, so we look at our data and it says there's 222 eruptions, and each eruption is giving us a piece of data. Remember, each one of these dots in here represents one eruption. So then what we have to do is ask ourselves, okay, where's the data coming from? Well, the data comes from the eruptions. Each eruption gives us a little bit of data. There you go. A lot of times it won't be as obvious what the observational units are. It maybe can be a little not clear. One way to do this, work backwards. What's my data? Okay, so then if that's my data, then one data point, where did that come from? And for us, it came from an eruption. Boom. So we got that down. The variable in this study. So write down variable. Again, if you're already there and you got this, great job. If not, that's okay. We go back. I mean, we're just starting off. It's perfectly fine to keep going back to try to find definitions of words. That's not a problem. Examples, not a problem. It's what you need to do. So we see that it says the recorded characteristics of the observational units are the variables of interest. Okay, so we had an eruption. What did we record from the eruption? All right. It also says some variables are quantitative, taking numerical values. Okay, and other variables are categorical, taking category designations. So the way that I think about categorical is boxes. Categorical variable, the possible answers or values to that you can put in these boxes. Yes or no box. They give some examples here. Eye color, green, blue, brown. There's mixtures like hazel, but you see the boxes. Marital status, married, single. So the boxes can be many boxes, doesn't have to just be two boxes, but each categorical variable will have boxes that you can put your values of the variable in. So remember, variables of interest are the recorded characteristics of the observational units. I know that the words can get a little blah, blah, blah as you're going, but that's okay. We just go down here and we can write things down to keep it all in front of us. We can look back in the book. So, whoops, don't scroll too far. It says the variable in the study, what are we recording from our observational units? AKA, what are we recording from our eruption? Well, this is where the picture's nice. Every dot in here is supposed to represent the time between eruptions of the old faithful geyser. So, time between eruption, that's your variable. It's exactly just your description of what did you pull out from each one of these units. Time between eruptions. There you go. And the nice part of this is it has that little answer for you. If it lets me click it. The observational units are the 222 eruptions, and the variable is the time until the next eruption, which is quantitative. So, whoopsies, forgot about that point. So this is quantitative, and it's quantitative because it's a numerical value in which I can take them and I can add to time between eruptions, and that makes sense. Gives me another time between eruptions, and that's a little more subtle of a difference that you're going to have to work on, but it's okay. We'll get there. So once we've got that point, that's good. And they start to kind of talk to us a little bit about what they are seeing, the authors are seeing from this data. So down here a little bit, I know I'm scrolling kind of fast, but we'll go back up. We see some numbers, so we'll go back to these numbers in just a second and kind of go back to our picture here. So it says the most obvious point is that it is not perfectly predictable, and I would agree with that. Go back up to this. These dots are kind of all over the place. Now, it's not too different between, low 40s and 95 minutes, but you can kind of get an idea of what that would mean to you if you went to go see this eruption and you get there and someone says, oh, the eruption happened 5 minutes ago. Well, okay. Are you going to be waiting 40 minutes for the next one? Or are you going to be waiting 90 minutes for the next one? That can be kind of a big deal for you. Maybe it's not that big of a deal, but that's an extra 50 minutes of possibly waiting around. So not a huge amount of time. They're still pretty close to each other, but definitely some difference between the results. So if we go back down here, it says not predictable. I think that makes sense from the picture. It's not all one perfect number. It's spread out a little bit. And the thing in your head that tells you, yes, not predictable, these numbers are kind of all over the place, that is variability. All right, and it says here it's the most fundamental property in studying statistics, and it's a very important point. The variation in the time. Again, if this was a perfectly predictable set of eruptions, this picture would be nice. It would be clean. There would be, if it's always one time, there would just be 222 dots on one number, and we would say, boom, easy, always, whatever minutes that is. But it's not that. It ranges from 40 to 95. There's a little more higher, some lower, but definitely spread out. So not predictable in the way that we say it's not predictable is that there is variability in here. So this is a very important word here, this variability, and they'll go down at the bottom. I guess maybe for you it's on the next page, and they'll talk about how we define variability. So we keep going, and then there's that word process that we've seen already once. It says we can view the times until the next eruption as observations from a process. In this case, we're gonna say that it's an endless series of potential observations. All right. So all they're trying to say is what we're doing is we're taking a small amount of eruptions, but these eruptions have been going on for a very long time, and will probably continue for a very long time after that. So we're only getting a little bit of information, and we're trying to make a claim from that little bit of information about everything, about the past, the present, the future, what is going to happen with this geyser. So that's an important thing to think about is we would never actually know the perfect answer to how long are things going to take between eruptions. It's not possible for us to know. And that's okay, but what we can do is use statistics to take a sample, take some of this small snapshot, and give ourselves an idea of what could be going on. All right, and so it goes on to continue saying that we have a representative view of the long-run behavior. This is key. Long run here is very, very important. So this thing says long run. That's going to be very important for us. We also want to make sure we know that this is a representative view, all right? Because if our snapshot was just a weird collection that doesn't really ever happen, we came on the day that the geyser was doing something crazy it never does. Well then, if it goes back to normal after the day we leave, then our data is not going to tell us anything about that geyser. So we want to be able to say or believe that our snapshot really does do a good job of saying what's happening in general over the very, very long term. All right. So it then continues to go through here and talk about what's going on. There's lots of things that could be determining how long it takes for the geyser to go. Lots of different things that we maybe can't account for. So, and that's okay. We're not doing statistics to be able to try to account for every little thing that makes this geyser go. That is physics and some other science that I don't know anything about that talks about what's happening, the mechanics of it exactly. For us in statistics, we're just trying to get an idea of the overall time between eruptions for this geyser without necessarily having to dig too deep on exactly what's happening. So we go down a little bit further, and we're reading through here, and they actually start to say some numbers here. So they say the shortest time was 42. So if we go down here and we look at our picture, we see that this first dot looks about 42, okay? And then it says the longest was 95 minutes. Again, if we go down here, we look, that's about 95 minutes. Okay, yep, we saw that. There appear to be two clusters of times. Okay, so this is a little tougher to see, but one thing you can do that's kind of neat is if you draw a line in here, it looks like I could be looking at two separate pictures. One to the left of 65 minutes, one to the right. And so that's what they're seeing here is there's two clusters, one from 42 to 63 minutes. So that would be this cluster, and the other one is from 66 to 95 minutes. That's this cluster there. So hopefully now that you're looking at that, you can see, yeah, there are two kind of groups of this going on. They say that the lower cluster of eruption times is centered at approximately 55 minutes, give or take a little. So this is a kind of tougher thing that we're going to have to talk a little bit about. How would we put some numbers on this exactly? But what you want to do is just basically look at the left side of this here. You know, if we just are focusing on this, the middle, what we mean by that is kind of the middle of the data. And so they say about 55 minutes. So if I draw a line in here, let's choose green. Those are dark colors. I wish they were brighter. So if I draw a line in here, yeah, about. You might think, there's some further to the left, kind of much further. And then there's also this big line right about 50, 51 that maybe you think it's a little bit further to the left. But we'll talk about what I just said and how that takes the middle and changes it a little bit later. So, okay, so they say the middle of that one's 55. If we keep going here, the upper cluster, they say, is 80 minutes about centered. And yeah, if we take this cluster, just focus on these, then yeah, this green line around 80 looks at about the middle. Okay, so try drawing that on your own while you're going through. Then, you know, take a picture of this, write it in your book, try to find the middle for yourself. See kind of where you think it is and if it lines up with what the book says. And if it doesn't, try thinking about that. Take that to your professor or another student that you're working with and see what they did and see why maybe yours is different than theirs. So it continues to talk about the overall distribution is centered around 75 minutes. So there's a lot more dots in this second group to the right. So then, to me, that says that the overall distribution, I'll make this a little bit thicker, nice, is at about 75 minutes. And that's a little tougher to see, and we'll figure out a numbers way to figure that out for ourselves. So then the last thing it says is in the lower cluster, the times are between 42 and 63, with most between 50 and 60. Yep, so they're kind of giving an idea here of, you know, one thing you could do is where's the middle of the data. Another thing you could do is where's the low end and where's the high end, and we've done all that. Another thing you can do is there kind of a cluster where most of them are, maybe in the middle somewhere, and that's what they're doing here. They're saying between 50 and 60 minutes. There's really kind of most of the data, so that would be in this cluster here, and I think that I would agree with that. It says in the upper cluster, it's between 70 and 85 where most of it is. And yep, I would agree with that. Kind of the chunks of the data go in there. So, you know, I agree with those things. So then it continues on after we put some numbers down just to see what's happening, and asks for what are the explanations. Well, so some of this, again, is physics and science that we don't necessarily want to get into. But it is important to think about what could be causing these times and their differences. So they mention that they have a thought that the variability in times might be explained by the length of the previous eruption. So, okay, that could make sense. If you have an eruption spewing out water for a long time, then maybe it takes longer to fill up. That is just a complete guess, knowing nothing about any of the science behind this, but that's okay to do. Try to think about what's happening here, on your own, and then what you can do is see if the data matches. So if we go down here, oh, look at that. It says exactly what I said. I promise I did not read that first, but either way, that's fine. So we go down here, and what they did was, and they're talking about it right here, It says, for simplicity, we categorize each eruption's duration as short, less than 3.5 minutes, or long. So what we're doing is, this is a very interesting thing, is we're taking the data, this original data, I kind of messed up my picture down there, so we're taking this data and we're seeing, okay, looks like there's two groups. Can we figure out a way to group the eruptions themselves, these 222 observational units, can we take those and group them so that if we separate them, we get two pictures that look like one the left side, one the right side? So as we go down here, this is what they do. They say, okay, short actual eruptions and long eruptions, let's separate those dots. So again, all of these dots here, all of these dots here and here are just from that big picture, the one that we put here. All we've done was we've said, okay, we know more information about the eruptions than just what's on this, so let's separate them into two data sets and look at the pictures separately. And you kind of get that idea. They're not perfect separations, but what we see is that the short eruptions had a shorter time between next eruptions, and the long eruptions had a longer time between eruptions, just kind of like what we thought. So there's a couple things that we can kind of go back to here, observations as they put it, about the distributions. Again, remember the distributions, that's our picture. That's our picture. So they talk about the shapes. So the individual shapes of each of these are no longer two blocks here, right? We now have kind of one nice picture for each of these. And again, they're not perfect, but we've got just kind of one block here and one block here, right? So that's, that's not too bad. As we go down, the centers of the distributions are very different. So again, this kind of comes from what we already saw when we were looking at things on the picture below. We saw that there were two kind of centers with two clusters. And so again, these have two different centers. One centered probably around there, another one centered probably around here. And look, those do not match up. And that's an important thing to see and try to get an idea about. All right, so we also have the variability in times until the next eruption. So then the variability, if we go back up here, again, they are different. So if we're looking at this, we see that this, this is the smallest, this is the largest, this is the smallest, this is the largest. This difference is bigger than this one, so that's one thing, all right? And I would also say it's not just the two bigger ones, but I would say this bottom one has more that are spread out than this one does. Most of these dots really are kind of packed tightly together here. A lot of packed in here. There are some packed in here. There's definitely kind of packing with these, but there's more dots that are spread out here. So we would say that this shorter geysers have more variability. There's more spread in the data. All right. And so looking through here, again, we're reading through this, but it's just saying the same things that we're saying as you're thinking about this. And then the first thing it does here is it kind of throws at you some very important things. It tells you how we measure stuff. So one way to measure the center of a distribution where we were drawing those lines is the average. So we've seen averages before, hopefully, but it's something that if you're like, man, I don't remember what this is, then that is okay, because what we can do is we can Google it. So we go here, we say, you know what, Google, I don't remember what an average is, so can you tell me? And then the Google says, okay. So right away, the dictionary definition, a number expressing the central or typical value in a data set. Yeah, that's what we're looking for. Okay, that's good. But, that doesn't tell us how to get it, right? So then the next thing we see we have a Khan Academy video, which Khan Academy is awesome. We've got one specifically labeled statistics we can click, and just one labeled average. We go down here, and Math is Fun is a very good website that I use all the time. So we go to this website. It says a calculated central value. Good, that's what we were looking for, right? That's really good. And then right away it gives us an example. So use the example. It says, what's the average of 2, 7, and 9? Pretend these are our data values. Well, the formula is take your data values, add them up, divide by the total number that you had. And so, in this class, sometimes we skip over a little bit having exact formulas. So we have them, but, we're not stressing them. But if you're a type of person who really likes to look at a formula to get an idea, and that can really help you, well, then go to your professor. The book sometimes has the formula. And if not, go to Google. Look this up. Try some examples. Look through the examples. Work on it your own, and see if that helps you get a good idea of what's going on. All right, so that's our average. It's kind of a way to specifically, just like we saw here, we can actually measure and get one single number for this. So we can do that for ours, and it did that. So down here at this table, we see an average or mean for all the dots, an average or mean for just the short duration, this bottom one, an average or mean for the long duration. And it's kind of where we put our line, so that's good. The next piece is, they say here, the more varied or spread out data is, the larger its standard deviation. So, again, you could do the same thing. We say, excuse me, computer, I do not know what this is. Please tell me. Standard deviation, right away. So it says a quantity calculated to indicate the extent of deviation. Okay. That's not very helpful, though it sounds kind of like what we're doing, so that's good. We see some nice pictures here. Again, Khan Academy, the standard deviation videos, very good, but look at this, Math is Fun. So we go to this, and we see, look at this. We have a measure of how numbers are spread out, perfect. And then we see a formula that's a little scarier looking. Now again, if you are okay with formulas, you like math formulas, well then dig right in. If you're not too happy with formulas like this, that's okay. I still think there's a lot of value in looking at the formulas. What you can do is just go to this example. Go to this example where they've got data values, and then follow the directions here. All right, see exactly what's going on. They've got another example out here where they've worked things out. It uses the average, so that's a key thing that sometimes if you're not looking at the formula, you might miss, like, oh, I needed the average to get the standard deviation. You do. So try some examples out. Again, in this class, it's not that important that you have this standard deviation formula memorized. We've got very powerful computers that can handle this no problem. But it gives you a good idea. Seeing some examples is a very helpful thing. And you will see examples of standard deviation, some picture examples that we'll go through. But actually crunching the numbers can be pretty helpful too. And they did this here for us. So there's a lot of spread when I put the two pictures together. That made sense. There, for the short duration, is not as much spread, the 8.5 minutes, but it's still pretty spread out. And then the long duration, just like we noticed, the spread is a little bit less. So these numbers that are calculated, they're lining up with what we had seen, which is great. So then we just continue to go down here. They're talking about the standard deviations of the next eruptions are smaller for the separate groups. We saw that just looking at the picture. And then what do we say here? So we noticed a trend. We noticed there were two kind of different groups and ideas here. And what that could do is really help us get an idea of how to predict the next time until an eruption based on now knowing the previous time. So that's an important thing that, we've really done a lot of work here to figure out that there's that connection. And so from that, we can put that all together. So then the kind of last piece here is what they did is they put all of the basic terminology together. So that's really important. I mean, you can go through and you can, mark up the book and say what terminology do I think is important. But they'll put it all together for you, which is really nice. They do the shape, which we've talked about. What's the picture look like? The center, we've talked about that. We looked at the picture, and then we also calculated the mean or average. The variability, how is it spread out? We looked at the picture and we got a standard deviation. And then unusual observations. We didn't quite mention that as much, and they're defining it here. But basically what you're thinking of are there observations that are far away from everything else? So if we go back up here, I think the one you might see kind of right away, there's two that you might check out. The first one is right here, and then the next one is here. So that's much further away from the middle than a lot of these other dots are, both of them. And so you might kind of think to yourself, what's going on there? Can we explore that point more? What happened? Was there an error recording? Or is there something else going on we're not really thinking about? So that's another piece to try to put together. And then they have one more think about it where you can kind of test yourself, which at this point I would definitely do if you go through and you don't get what they get for their answer, you go back up, you try to make the connections with this example, and then you're good from there. So this was 36 minutes, which is an infinite amount more time than I wanted to use. So I may try to cut this up or whatnot, or just dump it. So maybe hello void.